Welcome students to your last lecture annotation video. This week we will study about the topic channelization. So let's move on forward. We always move forward. We do not stay at a place more than it requires. So this is what data communication is all about. So the discussion points here is the multiple access as usual, and it is based on this protocol called channelization. The three main topics are frequency division multiple access, time division multiple access, and code division multiple access. So let's move on to the concept and example. So if there is a dedicated link between the sender and the receiver, then data link control layer is sufficient. However, if there is no dedicated link present, then multiple stations can access the channel simultaneously. Multiple accesses can decrease collision and avoid crosstalk. So that's the concept why we require this multiple access. So in a nutshell, we require multiple access because we want to decrease the collisions and avoid the crosstalks. We don't need that. It hampers the effectiveness of data communication. So there is in some topologies there is direct link between the sender and the receiver, and then that data link control layer is sufficient. But if there is no dedicated link in the majority of the topologies that we see, that we need the this multiple access protocol. So we go to the example. In a classroom full of students, when a teacher asks a question and all the students or stations start answering simultaneously, then that is sent at the same time, then a lot of chaos is created. Data overlap, data loss, data corruption, etc. Everything is about data corruption. Then it is the job of the teacher, the multiple access protocol, to manage the students and make them answer one at a time. So this is why this multiple access is needed. So I hope you get that. So I will just move on forward. So what do we mean by channelization? In real world scenario, if we see, when we watch TV, we see a single channel at a time. So this is what does we mean by channelization. So channelization is a multiple access method in which the available bandwidth of a link is shared in time, frequency, or through code between different stations. This is somewhat similar to the concept of multiplexing. So we will see it in a bit real soon. So these are the full forms: FDMA, frequency division multiple access; TDMA, time division multiple access; and code division multiple access, CDMA. So there would be a bracket right here. So I hope you get it. So let's move on forward. So at first we will see right here is the concept and the key points of the frequency division multiple access. So what does it focuses on? It is evident from the naming, is that it focuses on the frequency bands. Available bandwidth is divided into frequency bands, and each station is allocated with a band to send its data, so that it does not overlap with the data of other stations. A band is reserved for specific station all the time. That is, if I want to say, for example, you can reach me at my phone number, then it is reserved for my phone number only. If you call me and find other person other than me to answer the call, it will not be possible. So that is somewhat like this. So each station uses a bandpass filter to confine transmitter frequencies. That is, it catches the total signal and then filters it to receive its specified signal frequencies. So in order to avoid station interferences, allocated bands are separated from one another by guard bands. So this topic right here we have seen during the multiplexing topic. So these topics are very similar, as you can see. So let's move on forward. This is how the FDMA transfers the data. This is the common channel or total data channel, and this is channel 1 or station 1. This is channel 2 or station 2, and this is channel 3 or station 3, and this is channel 4. So data are transmitted from 1, 2, and 4, but silent is the third station. So FDMA specifies a predetermined frequency for the entire period of communication. So the entire period of communication, we are empowering the FDMA or multiple access protocols to maintain a specific frequency for each channel or band. Next, we stream data, a continuous flow of data that may not be packetized, can be easily used with FDM. This is what happens. Stream data is a continuous flow of data that may not be tokenized or packetized, and which can be used with the FDMA. We see this uses when we watch television, when we hear the different radio stations, etc. Similar like multiplexing. So this is what happens. So the next topic we will discuss about actually that what happens when we use this technique and what is the difference it has with multiplexing technique. So what happens here is that it's quite simple. FDM or multiplexing, frequency division multiplexing, is a physical layer technique. And what does this FDMA layer adheres to? It is the data link layer technique. So combine load from low bandwidth channel and transmit them by using a high bandwidth channel. This is the basic concept of multiplexing. But FDMA, what does it do? Each station tells its physical layer to make a bandpass signal from the data passed to it. So this is what happens. It instructs the physical layer that I will transmit it like this, and you should follow, or you should use this like this, or make a bandpass signal and then transmit the data. So this is what the basic differences between multiplexing and multiple access. So the channels that are combined are low pass, that is low frequency channels are combined, and then they are transformed into high bandwidth channel and then transmitted. The FDMA, in the FDMA, we see that the signals must be created in the allocation band. So that is what happens. We have seen right here that each station is given a channel to transmit it. So we move on to the next topic. The multiplexer modulates the signal, combines them, and then creates the band pass signal. So there is no physical multiplexer at the physical layer. The signal created at each station are automatically band pass filtered. So there is no need for the signals to be multiplexed, but it needs to be multiplexed in the multiplexing criteria in the physical layer actually. But in the specific data link layer, we do not need any multiplexing technique. So we have its own multiple access protocols that is very specified to this topic. The bandwidth of each channel is shifted by the multiplexer. The bandwidths are mixed when they are sent to a common channel. So what happens right here is that the bandwidths are mixed and actually they are sent together as the common data channel, as a common message, and sent throughout the channel. So this is what multiple access and multiplexing has their differences. I hope you get it. So let's move on forward. Time division multiple access. So here the time division multiple access is a channel access method for shared medium networks. It allows several users to share the same frequency. So it allows the several users, we can use the same frequency, but my time period is this, or my time slot is say for example from 12 a.m. to 2 a.m. kind of like this. So each station is allocated a time slot during which it can send data. Similarly, like the frequency division multiple access, it is somewhat similar to time division multiplexing. You are familiar with these slots, and each station transmits its data in its assigned time slot. This is what happens. So if we were to use time division multiple access while transmitting our television channels or cable channel networks, what would happen is that for 5 minutes we get to see the news channel, then for next 5 minutes we will see the sports channel, and then next 5 minutes we will see the history channel, and then the cartoon networks and so on. So this is the problem with the time division multiple access thing if we were to transmit or use it in our cable networks. So you are quite familiar with this scenario that this is the station 1, this is station 2, this is station 3, and this is station 4, and each has a different time slot, and which are combined in the multiple access and used as the combined data channel or combined channel to transmit the data. So the main problem, as I have discussed already, is achieving synchronization between different stations. So the issues remain the same. The synchronization is a very necessary topic in data communication, and specifically in this multiple access or multiplexing topic. So the synchronization is a must for this topic. So each station needs to know the beginning of its slot and the location of its slot. So it is a quite a difficult task if we were to design and inform the stations when its slot starts and the location, which slot it will be able to transmit it signal, etc. This is difficult because of the propagation delays introduced in the system if the stations are spread over large area. So this is a very interesting thing. This is difficult because the propagation delays introduced in the system if the stations are spread over large area. So if we say, for example, there are 4 radio stations in Bangladesh, only in Dhaka. But if we consider the whole country of our country, and we say, for example, we have incorporated 64 station in 64 districts, so it is very difficult and because of the delays of the transmission to reach us every corner of our country. So this is very difficult. To compensate this, we insert guard times, like the guard bands introduced previously during the frequency division multiple access. We use guard times that during this time no stations will transmit anything. So this is what guard times means. So it's in between the slots. These are kind of guard times. This blank white space between the time slot, these are the guard times. So I hope you get that. So let's move on forward. I'm saying this repeatedly that if you have any problem, feel free to discuss it with me in the Google Meet session. So I will look forward to our discussion. So this is the last topic of your syllabus, code division multiple access. So this is quite a lengthy topic. So I hope you will bear it with me. So at first, what is code division multiple access? So the premise is that the code division multiple access was conceived several decades ago, but only recently advances in the electronic technology have finally made its implementation possible. So it was thought out very theoretically, and it was introduced very early at early stage, but it is finally made possible only recently. So CDMA offers differs a specific thing which is different from FDMA because only one channel occupies the entire bandwidth of the link. So this is the total difference right here from the FDMA. And in the TDMA, because all stations can send data simultaneously, there is no time sharing. So this is what happens right here. That why do we need this CDMA, and why do not we need the FDMA and TDMA, and why they are kind of obsolete right now. This is what happens right here. The difference is right there. It's quite striking actually. So let's move on forward with the analogy. So CDMA means communication with different codes. So if I were to communicate with you guys in say for example in Hebrew with only one of you, and then in Bengali with other, and in English with another person, so it kind of it analogous to this CDMA protocols. So let's take a look at the example of the slide. So in a large room with many people, two people can talk in Bengali if nobody else understands German or Bengali. So this should be Bengali. So this is a correction right here. I hope you get that. So another two people can talk in French if they are only ones who understand French, and so on. In other words, the common channel, the space of the room, in this case, can easily allow communication between several people, but in different languages, which are analogous to codes. So this is what I have told you before, and it is kind of what's written in here. So I hope you get that, and this should be Bengali. This is a correction. I hope you correct it. So let's move on to the ideas. So the idea is that let us assume that we have four stations, 1, 2, 3, and 4, connected to the same channel. The data from station 1 are D1. This is not a derivative. That is or delimiter. This is D1, the data 1, and data 2, data 3, and so on. The code assigned to the first station is C1, code 1, to the second is C2, and so on. We assume that the assigned codes have two properties. If we multiply each code by another, we get a product of 0. If we multiply each code by itself, we get 4, the number of the stations. So this is the basic concept. So this is the basic concept right here. I think you get it. It would be much more easier if we go to the example right now. So this is the analogous example. If we take, for example, the data of station 1 is D1, the code assigned to it is C1, then the total channel, then the total data is D1 and C2. This is the total code word, and this D2 C2 is the code and data of code word of station 2, and so on. And if we add this total stations, all the stations code word to form this result, which is passed along the common channel. So this is what happens in this figure. So I'm just going to read about the point. Station 1 multiplies its data by its code to get D1 into C1. Station 2 multiplies data by its code to get D2 into C2, and so on. The data that go on the channel are the sum of all these terms. We add this D1 C1 with D2 C2, D3 C3, and D4 C4, and pass this total data in the common channel. Any station that wants to receive data from one of the other three multiplies the data on the channel by the code of the sender. So this is how it cancels the code word and gets the data. So for example, suppose stations 1 and 2 are talking to each other. Station 2 wants to hear what station 1 is saying. It multiplies the data on the channel by the code C1 of the station 1. So this is what happens. because the codes C1 into C1 is 4, but C2 and C1, C3 into C1, and C4 and C1, the multiples are all zeros. Station 2 divides the result by 4 to get the data from station 1 only. So this is what happened. The data D and this required station CJ is the example, and then we multiply it by other data channels, and we get this values of that data. So, and we use it to decode the data that was sent from station 1. So I hope you get that, but for clarification, please ask me in Google Meet or in or self-study from your book. So this how we generate these codes. So CDMA is based on coding theory. Each station is assigned a code which is a sequence of numbers called chips. So how do we use to form these chips? We use this. We generate these codes using these two basic rules. This is called. This is actually called Walsh table. The first basic rule is for 1. If we say, for example, if we have a matrix of row 1, column 1, and the value of the member of that matrix is +1 only, then we will get a twice of that value. This is the degree of the Walsh table. So we get +1 in this three spaces and a -1 in this. So if the value of n is, for example, 1, then we have to find the value of twice n, and it is shown in right here, the value of wn, wn, and wn, and this is the opposite or not of w1. So this is what happens, and this is the value of w4. So this here is the value of w2. This also is the value of w2, and this here is also the value of w2, and this is the not or opposite of w2. So there you have it, and each row is defined as a code for each channel or station. Say, for example, this is for channel 1, and this is for channel 2 or code 2. This is for channel or station 3, code 3, and this is for channel or station 4, code 4. So this is what happens and how we generate these keeps or codes. And if we multiply this any two codes together, we would see that the final result would be 0. So it's for your own understanding that I am giving you this exercise. So please perform it. And if you could not do it, please consult me in the Google Meet sessions. Thank you. Now, let's focus on about data representation. How do we represent the bits, and how do we represent silence? So what we are doing here is that for a data bit of 0, we are representing it by a data with the value -1, and a data bit of 1 as +1. And if there is no data to send, that is the station remains silent. The value is 0. So this is the data representation or encoding rule of this code division multiple access. So what happens here is that, say for example, station 1 is wanting to send a bit 0. Then it will send -1 as the data bit, and after multiplying it with the code, we get this result, and finally we incorporate it right here. But before that, we collect the products or results of data bits and code bits, chips of all the stations, and after adding them together with their place wise, say for example, this is -1 plus -1 -2 and plus 0 -2 and plus 1 will give us -1. So this is how these results are calculated. We maintain the columns for addition of these values and multiplications of these values respectively. So be careful about that. So after generating this, encoding this code, we use the signal levels. For the -1, a negative amplitude of is used, and for -1 and +1, negative and positive amplitudes are used, and this is the final combination of the results. We had the code -1, -1, -3, and a +1. If we add this together, it's kind of a bitwise addition. We have a -1, and then we have a -1, and this column gives -3, and this column gives us the value of +1. So this is the signal that we generate, and then we send this signal towards the destination. So this is how CDMA works. So this is the final topic of your syllabus. So for your exercise, please follow the given exercise of chapter 12 of your textbook. This would be your final assignment. So I will give you a time, let's say for about a week, to complete these exercises regarding this topic. So see you in your Google Meet session in your online class. Thank you. So this is me saying goodbye for this course. This is the last lecture annotation video. So thank you all. It's the journey that counts. I hope to see you all succeed and stay safe. I pray for you all. Thank you. Goodbye.